Okay, so let's remember what we're doing. We're talking about uniqueness of Fourier series, right? So, okay, so, and we were in the middle of this theorem that said the following, that if f is integrable on the circle, and all the Fourier coefficients, are zero, and f is continuous at some point theta naught, then f has to be zero at that point theta naught, right? And we mentioned that of course you've got the corollary that so if f is continuous on the circle and all the Fourier coefficients are zero, then your function's going to be zero everywhere. Okay, and so what this tells you is that if you have two continuous functions, you have two continuous functions that have the same Fourier coefficients. If you've got two continuous functions that have the same Fourier coefficients, then they must be equal to each other, right? Because then their difference would have Fourier coefficients of zero, right? Which means that the difference is the zero function. Okay, so this is right how the Fourier coefficients, under certain conditions, the Fourier coefficients uniquely determine the function, right? So Fourier coefficients uniquely determine the function. Okay, and so we're going to prove the theorem by contradiction. Okay, we're going to say, well, suppose that suppose the function is say greater than zero at that point. Okay, and without loss of generality, we'll assume that this theta naught is just zero. Okay, so suppose that your function is bigger than zero at zero, right? So so it's some positive value there, and since it's continuous there, you know that you can guarantee that it's bigger than zero in some little neighborhood, right? So by continuity, there exists a little neighborhood, negative delta, such that f of x is bigger than 1/2 of the value there. So it's not it's continuous there. So we know that we can find some little neighborhood where it's bigger than where the values are bigger than half of the value at zero. Okay. Okay. So now we're going to create a sequence of trigonometric polynomials that will sort of interact badly with the function. Okay, so much so that the integral of the function against the trigonometric polynomials that will go to infinity, right? Where it should be that because of the Fourier coefficients being zero, being all zero, it should be that the function is perpendicular to all trigonometric polynomials. But we're going to see something that violates that. Okay, so we now create a sequence of trigonometric polynomials follows. So trigonometric polynomials, namely finite linear combinations of the characters. Okay. And so we do go like this. We say, well, we're going to make the first one by taking just the cosine and shifting it up by a small number. Okay. So right, here's the cosine, right? And we're going to shift it up by some tiny number epsilon. Okay. So here is, let's say that this is negative delta, and this is positive delta. Okay. So we choose delta. I'm sorry. We choose so where this epsilon is chosen. Small enough that outside of the little interval, we have that the absolute value of p is smaller than 1 minus epsilon over 2. Okay, so if you think about it, what that means is that you look at cosine delta. You look at cosine delta, and then the epsilon has to be smaller than 2/3 of that difference there, but the difference between 1 and cosine delta. So as long as epsilon is smaller than 2/3 of the difference between 1 and cosine delta, then when you shift it up, by epsilon, then this is going to be smaller than 1 minus half that epsilon. Okay. Then the values here are all going to be smaller than 1 minus half the epsilon, right? So epsilon should be smaller than 2/3 of this. 1/2 epsilon will be smaller than that guy, right? And so when you shift it up by epsilon, this thing is still going to be smaller than still going to be smaller than 1 minus half of epsilon. Anyway, it's just a calculation. Yeah, Kai.
I was going to ask, should we choose epsilon less than 1/3 times that quantity?
That will also work, but 2/3 is the limit, actually.
Okay. Wouldn't that make... I thought that would make p exceed the bound over here, 1 minus. Okay, I must be misunderstanding. It's okay.
I don't think I'm wrong, but
I don't think you're wrong.
Okay. Anyway, in any case, choose an epsilon. You can choose an epsilon that works.
Yeah.
I'm pretty sure this is the right one. So choose an epsilon that's small enough that this happens, right? Notice that we need the absolute value of p to be smaller than 1 minus epsilon over 2. So we also need to talk about what happens when we're negative down here. But you're shifting it up by epsilon, so this is definitely going to be smaller than 1 minus epsilon over 2. Right? So we don't, this part is the easy part. This part just requires a little bit of arithmetic. Okay. Any case, yeah. Choose your epsilon small enough that this happens. Convince yourself later that this is possible. Okay, so, okay. Second, okay. So now, by the continuity of the cosine, we know that we can also choose a small eta. such that where eta is smaller than delta, and delta is smaller than pi over 2, incidentally. We can choose an eta so that inside negative eta, we have that p is bigger than 1 plus epsilon over 2. Right? Right. P is just the shifted cosine. Right? P is just the shifted cosine. You know, it's going to be 1 plus eta here. I'm sorry, 1 plus epsilon here. Right? And so, you know, we can choose some tiny eta. We can choose some tiny eta inside which it hasn't dropped by more than epsilon over 2. Okay. 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 So also notice that so the third thing to notice is that so right now we've got the deltas and we've got the etas, right? And between the two, so inside here, both P and F are positive. Okay, so that's just a sum. Okay, so now we create the trigonometric polynomials just by taking powers of P. Okay. So now let pk theta be P of theta to the k. Okay. Right. What's the point? That inside the eta neighborhood, you know, P is bigger than 1, and so it's going to tend towards infinity. Right. Outside of the delta neighborhood, the absolute value is less than 1, and so it's going to shrink to 0. Okay. So this will give us the contradiction that we're looking for. So let's estimate the integral of f against p sub k. Okay. So we break it into three parts. Right. So inside negative eta, outside negative delta, and in between. Okay. So inside negative eta, what do we get? Well, we know that right, eta, we're inside of the delta neighborhood, right? So f is bigger than this is going to be bigger than 1/2 of the value of 0, right? And then we've got this p to the k. Well, that's 1 plus eta over 2, bigger than 1 plus eta over 2 to the k. Do you think?
No, that's yours.
Oh, somebody drop?
Yeah. Thank you. You're good.
Thanks. Okay, so so inside the neighborhood, f is bigger than some value. P is bigger than 1, right? And we're integrating over this length, so we get this is bigger than pi times f at 0 times this thing to the kth power, and that's going to go to infinity. Right. So that goes to infinity. right? Now, outside of negative delta delta, we have that this thing is smaller than, well, we know, we use the triangle inequality, right? So this is smaller than, remember that f is Riemann integrable, right? So, and being Riemann integrable means that you're bounded by you have some bound, right? That you're a bounded function. Okay. So this is smaller than that bound on f times 1 minus epsilon over 2 to the k, right? And then times just the length of the integral, right? And so that's going to go to 0, right? Okay. And then we have the other part, but we know that the function is positive there, so we know that that remaining part what am I doing? Sorry, what am I writing? This should be negative eta to eta, and this should be like outside, so negative delta delta complement. Right. And then so the other part, the integral over the integral over those two intervals is still gonna be positive. Okay. So the integral over the integral over the other part is gonna be positive. I'm just gonna say it. Okay. So what happens, you see, that as k goes to infinity, this integral goes to infinity. Right. So that goes to infinity with k, but because of the because all the Fourier coefficients are 0, this should not this should be actually be 0. So yeah.
The two parts of the proof where we need continuity. Like the first one, the part where we bound f of x by 1/2 f of 0 near it, and then the second one where we use boundedness. Like, are those the only two places we need?
Well, that's actually not continuity, but just the Riemann.
Oh, I see.
Just the fact that Riemann integral functions are bounded.
Right, I see.
Yeah.
So it's really only this condition that wherever it's non-zero, it stays non-zero for a little bit.
That's right.
Okay.
Okay. Is that clear? Is that clear? Yeah,
why
Jake.
is f of 0 a lower bound on f?
We picked the delta so that near, like f of 0 is our non-zero point.
So
I guess that it's at least half the value. Right?
We assumed without loss of generality that it was positive there.
Oh, and the half is what? Okay, yeah.
Yeah. So we right. We're going for a contradiction. We say, well, suppose f is not 0 at some point. So in particular, assume without loss of generality that that's positive.
Yeah.
And then by continuity, you know that there's some neighborhood in which it must be bigger than half of that value. It won't decrease that much. Everybody all right? Okay. This I hope this should feel sort of like easy walking, like walking through a park or something like that. This is not. You've seen much harder things than this. All of you have seen much harder things than this. Okay. Okay. So we have this uniqueness statement, right? That we have that if the Fourier coefficients are equal, and the function is f and g are continuous, then f and g must be equal everywhere, right? So we have uniqueness as long as we impose continuity. So with continuity, we have uniqueness. Okay. Okay. But oddly, what we don't have is what we don't have yet. We don't yet have is does the Fourier series converge? Does the Fourier series recover the function? Does that Fourier series actually represent the function? Okay. So from what we just did, we can get the following corollary. Okay. So suppose f is continuous on the circle. Okay. And suppose that the coefficients are absolutely summable. Okay. Suppose that the coefficients are absolutely summable. Okay. Then in that case, then the sequence of partial sums actually converges uniformly. To f. Okay, so you actually do recover your function from the Fourier series. Okay, and the proof of this is kind of a little bit odd, but so the way you prove it is you say, well, look. Because we have absolute convergence, that means that that the Fourier series converges uniformly. Fourier series converges uniformly by the Weierstrass M test, right? Because we've got the this thing will give us the bounds that the Weierstrass M test requires, right? The Fourier series is of course this is this, right? And each of these guys is bounded by the absolute value of the Fourier coefficient. Right? So the Fourier series converges uniformly. These guys are all continuous functions, right? Each of these things, each of these half-erased guys, each of these things is a continuous function. So we've got continuous functions that are converging uniformly. So they'll converge to a continuous function, right? To a continuous function. Right. They converge to a continuous function. To a continuous function that has the same Fourier coefficients. That has the same Fourier coefficients as the function that we started as f, right? Well, since they're both continuous functions that have the same Fourier coefficients, they're the same function. Okay. Is that all right? It's kind of a funny proof. So you start off with your function, and you say, let's get the Fourier coefficients. Let's get the Fourier coefficients, and if the Fourier coefficients are absolutely convergent, then the Fourier series represents a continuous function with the same Fourier coefficients. So whatever that thing is, right? This thing converges to something, but that thing is continuous and has the same Fourier coefficients as f, right? So it must be f, right? So this converges to f. Okay. Okay. So yeah. So we actually can recover the Fourier. In this case, it's not just that we can. In this case, the Fourier series is the original function, which is nice. So that's assuming that the coefficients are absolutely convergent. Just as a side comment, you remember I was talking about LP spaces, right? LP spaces are these things where you've got functions, is pth power, where the LP norm is finite. Okay. There's sort of like the corresponding little LP spaces where you're talking about sequences. Okay. Instead of talking about functions on R, functions on Z. Say. Right. So here you think about you're looking at sequences whose pth power, right, whose little LP norm is finite. Okay. So and this is p bigger than 1. So what this is saying in that language is that if your function is continuous and the Fourier coefficients are in little L1, right? So the Fourier coefficients are in little L1, right? Then your Fourier series recovers your function. Okay. Okay, let's get back to it. So the natural question is, when are the Fourier coefficients in little L1? When are the Fourier coefficients in little L1? Okay, and so we have the following. Again, pretty straightforward corollary. It's not really a corollary, but just call it a proposition. If you have a function on the circle, and f is twice continuously differentiable, right? It's differentiable 2 times, and each of those derivatives is continuous. Okay. This is often abbreviated. F is in C2. Then, in fact, your coefficients are big O of 1 over n squared, right? So big O notation means that, so recall, if you haven't seen it before, we say f is big O of some other function as x approaches some value. If there exists a constant such that the limit of the quotient is smaller than that constant as x approaches that value. Okay, so as long as your function is twice continuously differentiable, then your Fourier coefficients are going to decay like 1 over n squared. That's what this is saying. Okay. Okay. So this like most things we're going to say today is pretty straightforward. The proof is just use integration by parts. So use integration by parts. Right. You say, well, look, the Fourier coefficient. Well, that's going to be 1 over 2 pi integral from negative pi to pi of your function against e to the negative I and theta d theta. Okay. You pass the derivative from this guy over to that guy. Okay. So, right. So you say, let's this is going to be your u. If in high school language, this guy is going to be your u, and this guy is going to be your dv. Right, and you pass the d from this guy to that guy. Okay. Actually, let me move the 2 pi over to this side, just to make it a little easier. Okay. So, right. So what do you get? You get f v. Right. So negative 1 over I again e to the negative I and theta to negative pi and pi. Right. Minus right. V du, right, so you get your V, again, you get the negative 1 over I n e to the negative pi. Right, so, high school. Okay, so you do integration by parts, right, you pass the derivative off to the other guy, and right, so you end up with this term. This term here vanishes, right? This term vanishes because it's 2 pi periodic, right? F was a 2 pi periodic function, right? And this e to the negative I and theta is also, right? So we just end up with this. That's nice. We can just pass the derivative over and not really worry about it. Okay. So then you do it again, right? Do exactly the same thing. You get negative 1 over n squared, negative pi to pi, f double prime e to the negative I and theta d theta. Okay, so what does that give you, right? That gives it to you right there, right? This is smaller than 1 over 2 pi n squared times this integral here. But this integral is bounded by just this, right? Because by the triangle inequality, take the absolute value of the integrand, this thing vanishes, and we get the absolute value of this thing. but this was the second derivative is continuous, right? So this is going to be bounded by some constant, right? And so you get some constant over n squared. Yeah,
That's because it's continuous on a compact set.
exactly.
Right, yeah.
Yeah. Okay, so that's done, right? Okay, so we see that being what you see is that being one-time differentiable tells you about the decay. It'd be 1 over n. Twice differentiable gives you 1 over n squared, and so on and so forth. Right. And so right. So you see that one-time differentiable wouldn't be enough to guarantee that the Fourier series converges back to it. Yeah.
But if you had only one-time differentiable, is that enough to say the coefficients are like little L2? Like if you're taking.
Yes.
Okay.
Yes. Yeah.
Cool. Yeah.
Yeah. Okay. 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 So let me throw in just one small thing here. So here's something that you're going to see in the homework. A kind of continuity called Helder continuity. So if there exists a constant A such that for all x and h, f of x plus h minus f of x is smaller than A times absolute value of h to the alpha, then we say f is Helder continuous of order alpha. And in the homework, what you'll see is that being Helder continuous of order alpha bigger than a half is enough to ensure that that the Fourier series converges absolutely. I'm saying that the Fourier coefficients converge absolutely, and thus the series recovers the function. Okay. 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 Now we're going to introduce something that you want to think of as a kind of multiplication of functions. Okay, so this is something called convolution. Okay, and this is a really central idea, a really fundamental concept in Fourier analysis. So here we go. You have functions f and g that are 2 pi periodic. So functions on the circle. Okay, but you think of them as on R. Okay. So the convolution, which one writes f star g, is defined is the function on negative pi pi defined as f convolved with g is the integral of 1 over 2 pi times the integral of f of y g of x minus y dy. So that's the value, that's the value. Okay, so a couple of remarks. One, it's an easy exercise in change of variables to see that this is commutative. Okay, that f convolved with g equals g convolved with f. Two, one way of thinking about the convolution is that it's sort of a weighted average. Weighted average. Okay, so like, if I think of the convolution, so let me write g convolved with f. Right, it's going to be g of y, f of x minus 1 y. Okay, so if you, for example, if you think of g as, say, the characteristic function of negative a half. Okay, so it's one, between, it's one on this interval and 0 elsewhere. Okay, when we take the convolution, so let that be g. Right, g is the characteristic function of negative a half. Okay. Well, when you convolve, right, you're going to get 1/2. You get this characteristic function y f of x minus y g y, right? Right. So that's just going to be the integral from negative a half to a half of, f x y dy. Right? So what is that? That's taking the point x, right, and then just integrating it over, you're just integrating over the interval from negative a half, x minus a half to x plus a half. Right? So you have your function, and you're integrating, when you take the convolution f against g at x, you get this. You just integrate the function over you get the average value over the interval, the unit interval centered at x. Okay. Now, if I change my g to like 1/2 of the characteristic function of negative a quarter, right? What's that going to be? That would be that when you convolve, then what you're doing is you're integrating over the minus a quarter plus a quarter interval, and you're dividing by the length of the interval, right? You're dividing by the length of the interval, right? Right. In other words, you're taking the average of the function over the smaller interval. Okay. So let me just ignore the 1/2 pi for the moment. Okay. Right. This is going to be the average of f over x minus quarter, x plus quarter. Right, and so, if you keep on doing that, right, if you take smaller intervals and keep on, what am I doing? This should be 2. Sorry. Okay, because you're dividing by a half. You're multiplying by 2. Right. So. So what you're getting is basically when you're convolving against, so here's my first negative a half, positive a half. Here's my first g function, right? here's my second g function. I make the interval, you know, half as short, but I make the function twice as tall. Okay, you know, continue doing that, right? So make it half as short and twice as tall. Every time you have these g functions have a mass of 1, right? And when you take the convolution against it, you're taking the average of the function over the interval of that length centered at the point x, right? So this you want to think of as some sort of like average of the function of f around x. Yeah.
What's your last choice?
Okay. So yeah, let me just quickly write down one more thing. So if we let d sub n denote the Dirichlet kernel and convolve against the Dirichlet kernel, well, that's 1 over 2 pi integral from negative pi to pi of f of y against the Dirichlet kernel, right? So we get e to the in x minus y dy, right? From negative n to positive n.
Yeah.
Right, and you can see where this is going, right? We can, because it's finite, we can change the order. We can pull out the summation, right? And pi to pi fy e to the in x minus y dy, right? I can pull out the e to the I. I can pull out this e to the I in x, right? Because it doesn't depend on y. So e to the I in x integral f of y e to the negative I in y dy. And you see what that is? That's the Fourier coefficient. Right? That's the Fourier coefficient. And so what we get, I'm sorry, with this thing, it's the Fourier coefficient, right? And so we get the nth Fourier coefficient of f e to the I in x summed from negative n to n. In other words, the partial sum of the Fourier series, right? So we can recognize the partial sum of the Fourier series is actually the convolution of the function against the Dirichlet kernel, right? Remember what the Dirichlet kernel looks like,
Yes.
right? It's this thing, and as it gets bigger,
Right.
we get something like this, but it goes high enough that the mass is 1, right? And so what you're doing is basically getting an average of your function that ought to tend towards the value of your function at that point. Okay, so that's what's going on.